we are group 7 and we have a project called Scalable Topology of a Rat Brain. This video is going to be in 3 parts. First, I'm going to talk about the data, the rat brain data we have gathered. Then Francesca is going to talk about the topology, what kind of topology aspects of this data are we interested in, and then Petter is going to talk about implementation. So how did we implement this in Scala to calculate these interesting topology aspects of the rat brain? Okay, so first, the data. The data, well, it's a rat brain or a small part of a rat brain. So it's 31,000 neurons that consist into 55 different classes. And a neuron basically looks like this. So it has a nucleus, basically the main part of the neuron. Then it's something called a dendrite that connects to other neurons. And then it has this axon, which is basically an arm that extends from the neuron. And then it connects over here to the dendrite of the next neuron. Okay, when this data was gathered, they use something called the NMC module, which basically says that 2 neurons are connected if the distance between them, like this and this distance, is short enough for it to be an axon connected to the other one's dendrite. So connected if close enough. So this isn't actually an 100% accurate picture of the rat brain. They might be close enough and not connected, but it's a good enough approximation. Usually, when you look at these kind of rat brain models, there are like 2 distinct kind of analysis you can do. You can do a low order or a high order. Low order is basically when you look at pairwise statistics. So you only look how many neurons are connected and so on and try to do conclusions about the brain from that. It's kind of easy and was basically the first analysis you could do. More and more, we're moving into higher order structure. Like this creates, well, they're connected and there are different, so it's basically a graph. So we can look at topology and graph aspects of this and ask like big picture stuff about the whole graph in itself. And from that, draw conclusions about how the brain works. And this project will be a high order. We will look at like the global topology structure of this brain. Okay. So our data process, from a GitHub link from Kieran Barber, which is a research student of RAS, they had downloaded the data there and provided us with scripts to create an adjacency matrix. So Kieran Barber's GitHub Python scripts creates an adjacency matrix, 31,000 times 31,000, which is basically zeros and ones, 1 if the 2 neurons are connected. This is kind of a sparse matrix. There are possibly billion or close to a billion connections, but only around 0.7% of all entries are 1. So it's kind of sparse. We upload this to Databricks and then we convert it. Instead of looking at this whole empty matrix, we convert it to an edge list. So basically just a list of all edges between these. So 0.7 times this close to a billion edges. And then we can feed this into graph frame and create basically a graph frame object that is our approximation of the rat brain. Now, Francesca will take over and talk about what interesting topology aspects we want to look at. What is interesting from both topology and biological aspects of this.
I will take over from here with some theoretical motivation for our project, and also to highlight one obstruction that one might encounter when addressing scalability while doing a topological analysis. So scalability in the topological context is related to a local versus global issue. Indeed, imagine that we start with a huge directed graph, like in our case, where the graph is obtained by modeling a rat brain, many rat brains, where vertices are the neurons and edges are the synaptical connections between them. So let's say that this is too huge for our computer, and we wonder if we can do several local analysis, subdividing the brain, the neurons, and so the directed graph in several parts, and then glue them together. Well, this is in general many times cannot be done. Let me show it with a very simple example. Imagine that you have this directed graph where and let's say that this is too huge, too big. So we consider a partition of its vertices given by these two vertices on the left and these two vertices on the right, and we study them, the subgraph defined by these two subsets of vertices, and we try to take the union then. So what we get is just these two directed edges, which you can easily see that it's definitely different from the starting directed graph. But this is also topologically different. In the end, the graph obtained in the left side has two connected components, while the second one has only one connected component, and its edges form a loop. So they are topologically very much different. There are several attempts to overcome this issue, and not only, also to relate local properties and global properties of, for example, a network like this one we are studying as well. And I put two references here that show this. In particular, in these two works, it's paramount to study one particular motif that can be found in directed graphs, in graphs in general, which is the number of cliques, or if you want to call them complete graphs, complete subgraphs, or also in general in topology they are called simplices, and are those subgraphs whose vertices are connected with all the others, so like edge, for example, or a triangle, or tetrahedron, and so on. Since we are in the context of directed graphs, actually, in this work, what the authors actually considered are directed graphs with one sink and one source. But it's a bit too technical. However, anyway, this this kind of analysis is done, for example, for classification purposes, or to understand how the brain processes information. And this is also in a reduced form. This is also the analysis that we try to perform with our code.
Hi, I'll talk more about the code we've written. Now, in our folder, we have 3 notebooks. Data processing, which Adam talked a bit about. Motif finding, which is the main one I will talk about. But we also have a graph string converter, which helps us to write code, since graph frames uses a domain-specific language. It converts then in a small adjacency matrix to Scala code. What we do here is we import the packages, we code for some special motifs. An important one here is count loops. If we can do that, we can then encode these complete graphs more efficiently. Otherwise, we would have to do filters here. Now we don't. So these are encoded. First, we find all matches, then we count them. That will be important for our discussion later. Here we can read the edges, read the vertices, and then store them in a graph frame. We can do this since we store them as a edge list and not as an adjacency matrix. You are able to store them on a single computer as an adjacency matrix, but it is very, very, very annoying. Now, let us look at some specifics of this graph. We do not have any loops, thus we can count via not filtering, or simplices via not filtering. This graph is connected, very annoying, and we can count some other interesting things. Now, for the actual counting of complete graphs. First, we can count K2s. That should just be the number of edges, which is the same number, so that's good. Then we can count the number of K3s. We can run this command, but after about 2 hours, it will give you an error message saying that you're out of memory. That is because in the case of K4, we get too many matches, so that storing all matches is very inefficient. Then counting them is, of course, then also quite inefficient. Thus, we would like an easier way of counting them. And here we can use some combinatorial tools, which these 4 people have already done and published an article, or sorry, not published, but there's an article on arXiv here, computing persistent homology of directed flag complexes. Thus, we can try to implement their algorithm in Scala and see how it performs versus theirs. Here is a direct implementation. What is noticeable about this is that it is very much parallelizable. This for loop here is the thing we can parallelize. It is also recursive, so we can do this several times if we wish. So this is a naive implementation. We have also implemented a parallelized version here. The problem with this is that we parallelize too much. We parallelize in each time we return to that for loop. The cost of starting new threads becomes way too heavy. Therefore, we have also implemented a version that only parallelizes once. Implemented functions so that we can call the other ones easier using a graph frame instance. So let us look at a small example that can be done more easily. This one can actually be done by hand, and we can count what is called effector or counting the simplices here directly. Then we can run now or 4 ways of counting these. The first one, the naive one, gives us this list, which is good. The second and the third one, you see we have an added 1 in the beginning. That is because they also count the empty simplices. The last one here, just directly doing everything, gives us the same numbers, 6, 11, 7, 1. This one will take a while to run. We did this not with the optimal one, but the one who parallelizes everything, and left it on for 2 days. It did not finish. This one might be doable. But this is also doable, as we said, in this paper. They use a way more specialized version, and where they actually store each edge as a bit rather than an integer or something else, making it very, very efficient. That is all I wanted to say. So now we talked a bit about how we go from a brain and to how we go from actual code telling us things about this brain. Thank you for us, and goodbye.